Hello and good afternoon, everyone. I'd like us to please welcome to the stage Christopher Ariza, who will give us a talk about elastic generators, flexible static typing with TypeVarTuple and Unpack.
Good afternoon, and thank you for coming to my talk today. I'm really thrilled to have the opportunity today to talk to you about one of the most interesting and powerful new features in Python's typing ecosystem, that is TypeVarTuple and Unpack. So this year we're actually at 10 years of doing typing in Python. Typing was introduced in Python 3.5 back in 2015. And the best way I think about typing in Python is really as an optional layer on top of the language, independent of the runtime. I think many of us have found that using static typing in our Python code improves the code's quality and improves maintainability, though it does take some effort. We have great tools to statically verify our types, like MyPy, PyWrite, and a few others coming online right now. And there's numerous tools to actually use those static types to do runtime validation, which is a great way to reuse the effort you spent in adding those types to get some runtime benefits. I think many of us would agree that typing in Python is still a work in progress. TypeVarTuple and Unpack are an example of the continuing innovation we see in the typing tools available for Python. So let's start off by considering what are elemental and generic types. So elemental types are the simple types you might be using already, where, for example, if we have a function here like this process function, it takes two parameters. We can type annotate them to show that x is an int and y is a float. Now, some types are more complex. Some types are composed of types themselves, and we call those generic. So for example, if I have a function here called process that takes a sequence, I can say what type of values we expect in that sequence. And in this case, I'm saying this is a sequence of integers. Some generics take more than one type argument, like dict. Dict here is shown to take an argument for the keys, which is a string, and an argument for the values, which is a Boolean. So generics are made concrete with type parameters. A generic unspecified needs to be concretized, made concrete by providing what the parameters are that that generic type is set at. Many Python, probably all Python containers now are generic. So when we use a list, we can say this is a list of string. When we have a set, we can say it's a set of int, for example. And Python abstract base classes are also generic. So we can talk about an iterator of float or a generic mapping from string to bool. Now, the way we define generics has changed, and it's a really nice change that happened in Python 3.12. Prior to Python 3.12, in order to define your own generic class, you would need to make a subclass of generic and then provide explicit typevar instances to that generic. So for example, here I'm creating two typevar instances, and then I'm defining a custom class, here it's a map, and I'm giving it those two typevar instances to generic, which I have to explicitly subclass. Then, once I've defined those typevars and the subclass of generic, I can use those typevars throughout my interface to express the type relationships in the overall class. Now, from Python 3.12, this has changed. We no longer need to subclass generic, and we no longer have to explicitly create typevar instances, which is really cool. This syntax, I think, is really elegant and attractive. No more typevar instances. Here, we just name our class, and with square brackets, we just give labels for the typevars, and for free, we get those typevar labels, which we can use throughout our interface, just as we used to when we had explicit typevar instances. So we might ask more from our generics. I've shown you a couple simple generic examples, but what more might we want to do with our generics? For example, might a generic be able to define the size of a sequence? Or might a generic be able to specify an ordering of types within a sequence? Could, for example, we specify, instead of just being able to specify that we have a sequence of the union of string or bool, we have both string and bool in a sequence, could we specify a specific ordering of string and bool in a sequence? Well, we get almost there, we get pretty close with the tuple. So the tuple generic is really special, and it took me a while to figure this out. It was kind of surprising at first, because the tuple, since early Python 3, has had this dual capability to do more than the list or the set or many other types built into Python. So a tuple can be made concrete in two ways. It can be a sequence with size and type ordering. We can specifically say that this is a tuple of 4 elements that are string, float, float, and bool. So we can very narrowly give a size and an ordering of types with a tuple. Alternatively, we can do something very different when we make the generic tuple concrete. We can say instead, this isn't a tuple of 4 types or 3 or whatever. This is a tuple of 0 or more of some type, a variable number of types. And so, for example, here, I'm showing that this generic tuple has been made concrete to denote that it will accept 0 or more string types. However, what if we want both? What if we both want explicit ordering and regions of 0 or more types? And what do we do if we want to take this special power of tuples? We want to take this special power of tuples and we want to use it in our own classes. Well, we haven't been able to do that until TypeVarTuple. So TypeVarTuple gives us the power to have that expressive flexibility of the tuple in our own custom classes. And coming with that is Unpack, which is a special, powerful feature to use within our TypeVarTuples. So TypeVarTuple was introduced in Python 3.11. It's defined in PEP 646. If you are using Python earlier than 3.11, you have backwards compatibility available through the typing extensions package, which is quite helpful. So TypeVarTuple is a new type of typevar. A good way to think about it is a placeholder for 0 or more concrete types. It's a variadic. It gives us variadic generics, which allow us to have a variable number of type arguments when we make that generic concrete. And as I've mentioned, it gives us that amazing tuple-like flexibility in our own classes. It can also be combined with one or more typevar, which lets us do even more sophisticated things in defining our generics. Now, Unpack is a component or a syntax, there's 2 ways to do it, for making a TypeVarTuple concrete. When we have a TypeVarTuple, we can give it explicit types like we did with the tuple, but we can also do something a little bit different. We can leverage the unsized sequence notation of a tuple. That is, when we want to specify that we have 0 or more of a type. Before Python 3.11, we need to use an explicit component, this unpack definition. And inside that unpack definition, we can provide a tuple, and we can use that unsized notation to say, in this case, 0 or more integers, or 0 or more of some other type. After Python 3.11, we got a new syntax. This actually looks really familiar. You might not think that this is a new syntax, but it is, and it's quite idiomatic. This star tuple notation is telling us that we're expanding the tuple out, and we're expanding out a place for 0 or more types, and in this case, integers. So today we're going to talk about these, what I call elastic generics, and see some examples of what we can do with TypeVarTuple and Unpack. We're going to start by looking at specifically the tuple, because there's quite a bit we can do with tuple, and once we understand what we can do with tuple, we're well prepared to look at TypeVarTuple. We're going to see some examples of defining generics with TypeVarTuple, and then we're going to look at what I think is a really compelling and idiomatic application of TypeVarTuple, which is specifying generic DataFrames. So, why me? Why am I here today talking to you about TypeVarTuple? Well, I didn't work on the PEP, I didn't work on the implementation or any of the supporting tools. But I do want to give special credit to the authors of PEP 646. It's a really interesting PEP. Go read it. Obviously, this took some work in CPython, in type checkers like PyWrite and MyPy, and typing extensions. So I want to show a lot of appreciation for the work that went into this, because I have a hunch it took a bit of work. For me, I am presently Chief Technology Officer at Research Affiliates, a finance firm in Newport Beach, California. I've been programming in Python now for 25 years, which is a kind of long time. I started out using Python for algorithmic music composition and computational musicology. I worked on a package called Music 21 back then. Since 2012, I've been building financial systems in Python, which led me to create an alternative data frame library called staticframe, built on an immutable data model. And it's from that work on staticframe that I long pondered, like, how can we do static typing with data frames in a way that's idiomatic and gives us the power of static typing, and we can use that within Python for both static analysis and even runtime validation. And I had searched for long to find an answer. How can we do this? And when I found TypeVarTuple, I said, yes, that is the tool I've been looking for. So that's why I'm here today, and I'm really happy to have the opportunity to share this with you. Okay, so we're going to start and dig into what we can do in typing with tuple. Tuple has a lot of powers. I've shown you two. There's some additional ones, and you might even be surprised what you can actually do when you make the generic tuple concrete. So since Python 3.5, we've been able to do the two things I already mentioned, where we can define a tuple either as an unbound sequence of one type, whether it's 0 or more integers, or we can define a tuple as an explicitly sized type that, in this example, has to be an integer, a string, and a float. Since Python 3.11, we get an additional power to tuple, which is that we can use the unpack notation inside a tuple to literally have it both ways. We can have explicit types, integer and string in this case, followed by a region of 0 or more of another type. Now, this might seem kind of strange, but if we think about a record of data where we might have a few identifiers followed by a variable number of floating point observations, for example, you can see how being able to define a type like this is really flexible and accommodates a lot of potential data representations we might have. So this gives us a range of options with the tuple. We have sized and ordered, we have unsized, and we can actually have them both at the same time. Okay, so let's look at some examples and how MyPy will evaluate these. So if we just want to define an interface here, I have a function here called process, and it's going to take a tuple that I've made concrete by specifying I want it to be of length 3, and I want it to have an integer, a string, and a float. So if I give such a tuple to this function, MyPy says that's great. However, if I give a tuple with an additional float, MyPy is going to fail and say this is an incompatible type. What if we want to define 0 or more of one type? Well, here in our function interface, we now make the generic tuple concrete by specifying that it is a tuple that consists of 0 or more floats. And now we have a type that can express sort of an elastic container of various size, but they all have to be floats. So if I give it a tuple with 2 floats, MyPy passes fine. If I give it a tuple with 0, MyPy is happy with that too. But if I have a string at the end of my tuple, MyPy is going to correctly complain. This is an incompatible type. Now, what about when we have both sized and ordered and unsized types? Well, we have a limit here. We can't go too crazy. We can only have one unpack region in our types parameters that we give to our generic. And if you think about it, that kind of makes sense, because otherwise parsing this out becomes insane. These ordered types can precede and or follow the unpack region, which gives us quite a range of flexibility. So here I'm defining a tuple that must start with an integer and then follow with a string and then have 0 or more floats following that tuple. So in this case, if I just have an integer and string, MyPy says that's great. If I have an integer, a string, and 3 floating point values, MyPy says that's great too. However, if I have a none in there, MyPy is going to correctly say this is an incompatible type. Okay, so now let's go on and show how to define our own generic classes with TypeVarTuple and harvest that power that we saw in the tuple into our own classes. So with TypeVarTuple, new generics, our own, can leverage this flexibility of the tuple. Again, a good way to think of it is kind of a placeholder. When we use a TypeVarTuple, unlike a typevar, we're defining a region, a space in our type parameters that can expand and grow depending on how we choose to make it concrete. Normal typevar can again precede or follow a TypeVarTuple, which gives us a range of flexibility. So this syntax has changed as well, just as I showed before. So prior to Python 3.12, we create an explicit TypeVarTuple instance, and then we subclass generic, giving it that TypeVarTuple instance. And again, we can then make this our own class now concrete with the same flexibility we saw in tuple, where I can make record concrete to say, hey, record only takes an integer and a string, or I can say this record, this different record, I want this type to be represented as having an integer and a string followed by 0 and more floating point values. From Python 3.12 and onward, we get to use the very nice, very concise syntax where we no longer have to create an explicit TypeVarTuple instance. Instead, all we do is provide an evocative star in front of our name, which suggests that we're doing some TypeVary unpacky thing going on here. Right, so we can make this concrete by again, providing an integer or string, or saying, hey, we want an integer string, and then 0 or more floating point values. Okay, so let's look at a class. This class is using a TypeVarTuple to say this is a generic record, and we're going to just take that value and we're going to store it inside an instance attribute of this class. And again, we can imagine that we're representing data where we might have fixed expectations, that we have maybe certain labels, for example, an integer and string, and in this case, just one float. So we can say, this versions of record must have these 3 types. And in this case, we only want 3. If we provide an additional float, MyPy will say, this is an incompatible type. Again, we can take that flexibility and we can make this record class concrete in a different way. We can say, here, I want record to accept a variable number of type, and in this case, they have to all be floats, and I'll accept 0 or more floats. And so if we give it a tuple with 2 floats, that's fine. No floats, okay as well. But if we throw a string in there, MyPy is going to correctly say that's an incompatible type. Now again, we have the power to do both at the same time, and here's where things get really quite interesting. So I can make my record class concrete by saying it must start with an integer, it must end with a string, but I'll accept any number of floating point values in the middle. That's really cool. We have this sort of expandable region in the center of our sequence that can accommodate 0 or more floating point values. So for in this example, I give a tuple of an integer followed by 2 floats followed by a string. MyPy is fine with that. Or I can entirely leave out the floats, because remember that unpack region is 0 or more. If, on the other hand, I throw a Boolean at the end, that's not permitted, MyPy will correctly fail and say this is an incompatible type. Now, as I mentioned already, we can go even further, and in defining our generics, we can combine typevar and TypeVarTuple, which gives us even more flexibility in specifying our generic. So in this implementation called tagged record, we're imagining that we want to provide a tag, which might be an index or a label or some other identifier, as well as a sequence of values. And we want this class to be entirely generic so that we can use this, we can build these records to be specialized for various types. So now, if I want to make tagged record concrete, I need to specify first a type for the typevar, here given as string, and then the following arguments all are scooped up by the TypeVarTuple. The first one requiring a fixed string, and the remaining components being 0 or more floating point values. So if I try to create an instance of tagged record and give it to my process function, where I have a string for the first type parameter, and then the second TypeVarTuple consists of a string followed by 2 floats, MyPy is fine with that. But if I happen to throw in a string in that second argument, MyPy is going to fail and tell me this is an incompatible type. All right, so now we can talk about what I think is a really compelling application of TypeVarTuple, which is implementing generic data frames. So a lot of common usage of data frames in types is what I would say shallow. So many of us have probably seen functions that look like this, where we have parameters that say, hey, we're going to take in a data frame, we'll take in a series, and we're going to return a series. Well, that's nice, but we don't know anything about the values inside those containers. These are not simple types. These are complicated compound types that have many types within them. And the typing as such, I think, is really quite insufficient. When we think about data frames, they truly are generic, and they're generic in quite a few interesting ways. We can think about a data frame being generic to its index. What sort of values are in the index? Are they dates? Are they strings? Are they numbers? We can think about the types of the columns. Are the columns strings, or are they numbers or something else? Data frames can accommodate all these different presentations. But most important, data frames have variable numbers of columns, and those columns are often of different types. And actually, you might already start to see that, yeah, some data frames might have some expectations that the first 2 columns are strings or integers, and the remaining columns are floats. And we might imagine we have functions that are able to consume data frames that have variable numbers of columns of floats. These data frames are well defined in their types, but up until TypeVarTuple, we really haven't had a way to make a generic data frame that can accommodate all of those types of data frames. So this led me to implement what I think really is a comprehensively generic data frame, and this was released in Static Frame 2. This leverages TypeVarTuple to accommodate variable specifications of columnar types. So again, it's specifying the types of the columns of a data frame that's really a particular problem. You could imagine you create a generic that has 4 type vars for your columns, and you only get 4 columns and 4 types. That's not good enough. We want to be able to express, maybe we have 1,000 floats and columns of floats, and we don't care exactly how many they are, but we want to assert that they're all floats. Or we might want to assert that a data frame has a very specific ordering of types. By doing this, we can statically verify with MyPy and Pywrite, our interfaces, showing us if the data frames have the expected types. And Static Frame even implements an additional runtime checker that can use these types, can use TypeVarTuple generics to actually do runtime validation as well. This is all integrated with both generic series, generic index, and generic index hierarchy, which give a lot of typing opportunities. So how do we define this generic data frame? Well, it's actually pretty simple and elegant with the power of TypeVarTuple. We specify that this is a generic frame that has a traditional type var for the type of the index, a traditional type var for the type of the columns, and then a TypeVarTuple that gives us the full expressive capability of TypeVarTuple to specify 1 or more explicit types, or an unpack region, or combinations of explicit types and unpack regions. So for example, let's look here where we make a data frame concrete using Static Frame. So first, we could define that this function is going to take an argument, and that argument is going to be a frame, and we can say explicitly we want the index to be a date, we want the columns to be strings, and we want, the column labels to be strings, and we actually want the columnar data types to start with an integer and then have 0 or more floating point values. This, of course, is what I was doing before with tuple, with my record class. But here we're doing it with a data frame. And again, this is actually a sensible sort of idiomatic representation. It's not uncommon for us to have functions that process data frames where we have strong expectations that maybe the first column is an integer, the second column is a string, and then we have 1 or more floating point observations that follow those identifiers. So once we've made the frame concrete as such, we can pass it some values and see if it works. So here I am creating a frame that I have to explicitly type because I can't automatically derive these in a way yet. But I want to explicitly say this is a frame that has an index date for its index. The column labels are strings. And in this frame, we have an integer followed by 3 floating point columns. That's actually how we create that frame. And then we can give that to MyPy, and it will pass. Now, in this example, it's sort of trivial because you see the code right next to each other. But imagine the frame is declared far from this somewhere else in your code, and it's being consumed by a function somewhere else. Through this static typing, we can evaluate if we have a mismatch in that in static analysis, which is really quite powerful. On the other hand, if we created a data frame that consists only of columns of an index, of an integer, of a float, and a string, there we would have a frame that violates the concrete frame that we've assigned to our process function. And now, if we were to give that frame to our process function, MyPy would fail and say, this is an incompatible type, and that's exactly what we want. So I hope I've convinced you that static typing can be elastic. When we think of static typing, we think of fixed things. And prior to TypeVarTuple, the type parameters to generics were fixed and static. So what we have with TypeVarTuple is something that's really interesting. We have static typing that is variadic, that can have we can define generics that can accept variable numbers of type parameters, and offers us really a new opportunity to describe generics in a very flexible way that I think accommodates many real-world situations, real-world data representations that we have to deal with. So again, it's TypeVarTuple that gives us that flexibility and offers some really great new opportunities. In addition, I've shown you how we can use TypeVarTuple to solve a problem of static typing of data frames. Data frame columnar types are variable. Sometimes we have a data frame that has only 4 types. Sometimes we have a data frame that we want to have a variable number of floating point columns, for example. With TypeVarTuple, we can actually make such generic data frames and use them for static type checking. All right, thank you for your attention. I have if you're interested in learning more or seeing more examples of this, I have 2 articles that go into additional detail. We maybe have a couple minutes for questions, so I'm happy to take any questions now, or feel free to find me around the conference and talk more about static typing. Thank you very much.
Please line up in front of the microphones if you have any questions. We have 3 minutes.
Hi. So I think I understood you to be saying that when you have one of these regions that's flexible, you can only have one of them in your data
Generic. Yes. Yes.
So unfortunately, I have several use cases where I want multiple of those, and in fact, I also want to enforce relationships among how many of each of them there are.
Yeah.
Is there anything on the horizon for that sort of problem?
Not that I'm aware of, well, yeah, not that I'm aware of in general. I think in the one thing you might do when you want 2 typevar regions really is have 2 other types that sit there and make each of those compose within a typevar tuple. So it's not flat, but you would have to bundle it. That's one way I think might solve your first problem. Your second problem, I don't know how to solve that yet.
Okay. I can provide use cases if you're interested.
Yeah,
but
yeah,
I'll
sounds
let
interesting.
Someone else ask.
Great, thank you, thank you. All right, thanks everyone.